Have you ever stopped to wonder why your hair clumps together when it's wet? Or why water just seems to play by its own set of rules? Well, today, we're pulling back the curtain on one of chemistry's biggest secrets, a tiny little force that has a massive impact on everything. Let's dive deep into the hydrogen bond.
But hey, before we get started, let's talk about how you're going to really lock this knowledge in. To truly master concepts like this, you've got to practice. So for all you SPM students out there, I seriously recommend you check out MCQ SPM.com. You can just scan the QR code right here on the screen or download the MCQ SPM app from the Google Play Store. It's packed with past-year questions that will get you ready for the real deal. Okay, with that said, let's get back to the chemistry.
So, let's kick things off with some of chemistry's little everyday mysteries. What's the secret force hiding in plain sight, making things happen that we probably never even think to question?
I mean, really think about it. You hop out of the shower and your hair just sticks together in clumps. Or you're trying to flip the page in a book, and what do you do without even thinking? You wet your finger, just a little. We all do it. But what is the actual science behind that? I'll tell you, it's not magic. It's just really, really cool chemistry.
And the answer to all these little puzzles is the star of our show today. So let's meet the hydrogen bond, the invisible force that's secretly running so much of the world around us.
All right, let's get the official definition down, shall we? So what exactly is a hydrogen bond? It is an intermolecular force. Now listen closely to that word. It means it's a force between different molecules, not the covalent bonds inside a single molecule. That is such a common mistake people make in exams. This is a special, extra strong attraction between a hydrogen atom in one molecule and a very electronegative atom, we're talking nitrogen, oxygen, or fluorine, in a totally separate molecule.
Think of it like a recipe. To cook up a hydrogen bond, you just need a couple of key ingredients. First, you need a hydrogen atom that's already bonded to an electronegative atom. And second, you need another super electronegative atom nearby. For your exams, just remember the big three: nitrogen, oxygen, and fluorine. You put those things together and bam, you get this incredibly powerful invisible attraction between the molecules.
And this image shows it perfectly, using the most famous example of all, water. So in a water molecule, H2O, that big oxygen atom is super electronegative, right? So it's greedy. It pulls the shared electrons a little closer to itself. This makes the oxygen part of the molecule slightly negative and the two hydrogen parts slightly positive. And it's that slightly positive hydrogen that gets attracted to the slightly negative oxygen of a neighboring water molecule. That little dotted line, that attraction, that's the hydrogen bond.
Okay, enough theory. Let's see this bond in action and check out some of its everyday superpowers. This is where it gets really fun.
So let's solve mystery number one, the wet hair. Your hair is made of protein molecules. When you get it wet, the water molecules start forming hydrogen bonds with those protein molecules. They're basically acting like millions of tiny little magnets, or a molecular glue, pulling all your hair strands together. It's as simple as that.
And what about turning the page of a book? You guessed it, it's the exact same principle. Paper is made of a substance called cellulose, which, just like the protein in your hair, can form hydrogen bonds. The little bit of moisture on your finger introduces water molecules that create hydrogen bonds with the paper's cellulose. This bond gives you that tiny bit of extra friction you need to get a grip and separate the pages. Pretty neat, huh?
Now this is a classic SPM question. You will see this. Why is the boiling point of water so unusually high? To really get it, let's compare water to something like methane. They're both simple molecules, but water boils at 100 degrees Celsius, while methane boils at a ridiculously cold -161. So what's the difference? Well, methane molecules are only held together by weak forces called van der Waals forces. But water has those weak forces plus all of those much stronger hydrogen bonds. So to get water to boil, you have to pump in a ton of extra energy to break all those strong hydrogen bonds. The main takeaway here is, stronger forces between molecules always means a higher boiling point.
All right, let's switch gears and put on our exam hats. We've got the concepts down, but now we need to know how to use them when the pressure's on. This is all about cracking the exam code. It's about strategy.
So here's a real question from an MRSM paper back in 2020. It says, the boiling point of bromine is lower than iodine. Which statement best explains this phenomenon? Now notice, the question doesn't even say the words hydrogen bond, but it's testing the exact same principle of intermolecular forces.
So how do we tackle this without getting confused? You follow the steps. 1. Identify your molecules. We've got bromine and iodine, both in the same group on the periodic table. 2. Compare their size. As you go down a group, the atoms get bigger, so iodine is definitely bigger than bromine. 3. Relate that size to the strength of the forces between them. For simple molecules like these, bigger size means stronger van der Waals forces. And finally, step 4, connect the strength of the force to the boiling point. Stronger forces need more energy to break, which means, you guessed it, a higher boiling point. So, the correct answer is that the forces of attraction are weaker in bromine. And here is your big takeaway rule for exams. For simple covalent molecules in the same group, as the size of the molecule gets bigger, the intermolecular forces get stronger and the boiling point goes up. You need to lock that logic into your brain.
Let's do one more. This time it's about solubility, from a Johor paper in 2024. The question asks, which of the following explains the statement, ethanol is a covalent compound which dissolves in water? See, this brings us right back to our hero, the hydrogen bond.
The whole concept here is solubility. Why does something like ethanol mix so well with water? Well, think back to our recipe. Ethanol has an oxygen atom bonded to a hydrogen atom, and of course, water does too. This means ethanol molecules are able to form those special hydrogen bonds with all the water molecules around them, and not strong attraction is what allows them to mix together so easily. So, for this question, the correct options are 3 and 4, which basically say that ethanol can form hydrogen bonds with water. And here's your takeaway rule for solubility. Substances that can form hydrogen bonds, like ethanol, will almost always dissolve in other substances that can also form hydrogen bonds, like water. It's a special version of that like dissolves like rule you might have heard about.
So there you have it. We've cracked the case of wet hair, of turning pages, and why water is just so weird and wonderful. The hydrogen bond is this incredible, invisible force that's shaping our world, from a single drop of rain to the very DNA inside ourselves. So now that you're in on the secret, my question for you is, where else are you going to spot the hydrogen bond at work in your daily life? Keep your eyes open because the chemistry, well, it's absolutely everywhere.